Nobody's thought of it. No one's paying attention. Hey everybody. So, what must be done to a capacitor in order to increase the amount of charge it can hold for a constant hold? Good morning, everybody. Thanks, guys. Do want to remind you guys that your exam is coming up. It's not that long from now. I think it's after Mardi Gras. Am I right about that? I'm pretty sure. Is this on the back of your workbook or it's in the syllabus in the front? But it's not that far away. It's a couple of weeks, really. 3 weeks, or 2.5 weeks or so. All right, so if you have capacitors, what can you do to the capacitor in order to increase the amount of charge that it can hold? All right, let's stop at 135. 135. Just guess if you're not sure. Just a few more seconds. All right, that's good. Either A or B. Remember our capacitance, C, is equal to kappa epsilon naught A over D. You have to use this, by the way, on the tutor assignment that's due tonight. And don't forget that kappa, that's your dielectric constant. And there is a problem where it has a dielectric in the capacitor that's made out of, I don't know, nylon. You know the question I'm talking about? There's nylon in between the plates. You have to look up the dielectric constant of nylon. It's in the OpenStax book. And include that dielectric constant, okay? And also, on that quiz, let me just point out a couple of things, because I've seen some students that have come by, and they've been telling me that 2 kilometers squared is equal to 2,000 square meters. But that's not true, right? It's actually 2 million square meters, because you have to square your conversion factor. Be very careful. There are several places in that tutor assignment tonight where you have to change your units to SI units. And if you don't do it properly, then the answer doesn't come out right. But you do get an answer. It's just not the right answer. Okay, so just be very careful with your units on that. Especially, this is the one with the cloud, I think. And it asks for the capacitance of the system. All right. Parallel plate. We haven't done these, have we? Okay, parallel plate capacitor has an initial voltage of 400 volts, and it stays connected to the battery. That means that the voltage will remain the same. If you double the plate spacing, that's the distance between the plates D, what happens to the voltage or the charge? How do they change or not change? You double the plate spacing, that means D, you separate them by twice as much. All right, let's stop at 105, a minute 5. Okay, awesome. C is right. So if I have a constant voltage, the battery is on there, so that means that this always remains the same. So I can get rid of B and A. The voltage isn't going to change, but something will happen to the charge. If I double my plate spacing, that means my capacitance goes down by a factor of 2. And if I decrease this by a factor of 2, that means that Q decreases by a factor of 2 as well. Did y'all put, was it D that you put? Yeah, C rather, yeah, C. So the charge decreases. Right. This isn't a joke, but it's just sort of a funny story. I used to be a bartender at, where's my name? At Harvey's. You ever been to Harvey's in Columbus? I mean, Starbucks. But anyway, one time this guy comes into the bar. It's a nice restaurant, sort of like Flanagan's, and he comes into like the bar area, and he has these jumper cables, like hanging around his neck. I guess maybe his car broken down. And I said to him, "You can come in, but you better not start anything." And that was a joke. I actually was a bartender at Harvey's, but I didn't say that to anybody. That would be kind of strange. All right. No, I just made that up. That would be good. All right. Now I charge a capacitor with a battery of 400 volts, and then I disconnect it. That's the great thing about capacitors. You can charge them, and then you can disconnect them, and you carry them away with you, and you have charge on this capacitor. Now, what if I double the plate spacing? What is the new value of the voltage? All right, let's stop at 1 minute. 1 minute. One minute. Okay, good. D is right. Let's look. So if I double my plate spacing, so that means this goes up by a factor of 2. That means my capacitance goes down by a factor of 2. And if my capacitance goes down by a factor of 2, I have whatever charge I have on this capacitor. That's going to remain constant. So this is constant. That means my voltage has to increase by a factor of 2. So whereas I had 400, now I'm going to have 800 volts. So D is the right answer. What is the equivalent capacitance of this combination? The equivalent capacitance. I have 3 capacitors. Each of them have a capacitance C. And they're all identical. What is the equivalent capacitance equal to? And do you think this tie goes in this shirt? I'll be honest. No. My daughter said yes. And generally I trust her fashion sense more than my wife. She said she didn't. She said the last one. So it's not working. But I went with my daughter. But I told her that I'd ask y'all. And you were saying what? As a whole? Yes. Yes? You're saying yes? Awesome. That's great. Like it's trend setting, right? Everybody's going to start wearing this. Just answer the question. What is the equivalent capacitance? All right. Let's stop at 110. 110. 110. Just a few more seconds. That's a good job put. Hey, goodness, that's good. All right, so look, I have I do this first. That's really good. I have 1 over C plus 1 over C. That's 1 over 2 over C, which is C over 2. And then I have, 2 capacitors in parallel. I have C over 2, and then I have C, and so the combination of those is going to be 3 halves C. You'll certainly have some questions like that on the test in a couple of weeks. how does voltage 1 across the first capacitor compare to voltage 2 across the second capacitor? How does the voltage across this capacitor compare to this capacitor? Is it equal, bigger, smaller, or is it 0? All right, let's stop at 45, about 10 more seconds. A few more seconds. Okay, good. B is right. In fact, what is the voltage across this capacitor? 10 volts. Right. I have 10 volts here. Because I have two parallel branches. Parallel branches have all the same voltage. So I have 10 volts here. And then across these two capacitors, I also have 10 volts. But because they're identical, each of them has what? 5 volts. That's right. Okay? Knowing how those voltages sort of split up will really help you on the test. We'll do some more on some of the old tests in the back in just a few minutes. What is the current? What is that? Is that somebody or is that a fire alarm? Is that you, Sheldon? How does the charge on the first capacitor compare with the charge on the second capacitor? So how does the charge Q1 compare with Q2? Equal, bigger, or less than? All right, let's stop at 35. 35. Okay, awesome. B is right. I have a voltage of 10 volts here and 5 volts here. Remember, Q is equal to CV. So the one with the bigger voltage, the one with 10 volts on it, has twice the charge as the one with just 5 volts. They have the same capacitance. So this one actually has 10 microcoulombs, and this one will have 5 microcoulombs. I think that's the last one here, right? Yeah, go to the back. You have some old exams in the back? I want to do a few more circuit problems just for practice before we move on to the next chapter. So let's do this, let's do number 3 first. Number 3 over here. I want you to tell me what is the charge on the 6 microfarad capacitor. That's the one on the right here, number 3. What is the charge on the 6 microfarad capacitor of a 3 and a 6 in series, hooked up to a 12-volt battery? What's the charge? I think this is exam 2. First you need to find, well, there's an easy way and there's a hard way. The hard way is to find the equivalent capacitance, then find the charge on that equivalent capacitance, and then that charge will be the same as here and here. Or another way, this might be a little easier, is to just look at it and say, how are the voltages distributed across these two different capacitors? I know they have to add up equal to 12, but which one gets the bigger voltage, and by how much is it bigger? And then once you get the voltage, you can multiply it times C, to get Q. Q is equal to CP. If you finish number 3, go on to number 1, because I'm going to ask number 1 next. But right now we're looking at 3, and we'll do about 10 more seconds on this. So going to about 150. And if you finish number 1, then go on to number 2. All right, stopping now. Okay, good. C is right. Yeah, we're doing well on this. So I'll do it the hard way first. The equivalent capacitance, 1 over 3 plus 1 over 6 is 2 microfarads. The equivalent charge, that is the charge on that equivalent capacitance, is 24 microcoulombs. And then you say, capacitors in series, what do they have, the same voltage or the same charge? Capacitors in series have the same charge. And so whatever the equivalent has is also what the 6 microfarad has. That's what I put right, see? Yeah, so another way to do this is you could say, what is the voltage on these? Well, I know the small capacitor carries a big voltage, and the big capacitor carries a small voltage. And I know they have to be distributed 8 and 4, because they have to add up equal to 12. And one of them has to be twice that of the other, because the capacitors are different by a factor of 2. And if I get the voltage, I can say the voltage times the capacitance, and that also gets the charge. 4 times 6 is 24. Notice my micros sort of carry through. Now let's try number 1. What is the equivalent capacitance of this? You want to start with the smallest part that's either parallel or series, and then combine that, and then move outward from there. And if you finish 1, go on to number 2. Feel free to ask your neighbor if you're uncertain what they think the answer is. Let's stop in about 10 seconds. Stop at, say, 120. 120, just a few more seconds. Listen, I guarantee that as you practice this more and more, you will get better at it. And you'll be able to look at this circuit. You don't even put your finger on paper. And you'll be able to tell me that a 3 and 6 in series is equal to 2. And then a 2, a 1, and a 3, well, 2 plus 1 is 3, plus 3 is 6. So this whole thing simplifies to 6 microfarads. I'll write this down. This whole thing simplifies to 6 microfarads. And then I have a 6 and a 3 in series. Well, we know that's 2, right? So the answer is 2. You just write that down in longhand. If you can't look at it and say that, that's okay. You can go through and you say, well, this is 1 over 3 plus 1 over 6, and that's equal to 2. And then I can redraw it. Where I have a 3, a 2, a 1, and a 3. And then the 2, 1, and the 3 go to 6. So I have a 3 and a 6 microfarad, and then those combine to give me 2 microfarads. Now, I want to know what is the voltage across the 1 microfarad capacitor. So what is the voltage here? Is it 3, 4, 6, 8, or 12? What is the voltage across the 1 microfarad capacitor? A3, B4, C6, B8, or E12. You will have a series of questions like this on the test, and it'll be a similar difficulty in the circuit, where I ask you the charge or the voltage or the energy through that across the capacitor. All right. Let's stop at 1 minute, so just 5 more seconds. Man, you're awesome. B is right. The quick way to do this is to say, well, I know I have 8 volts here and 4 volts here, because those two capacitors are different by a factor of 2. Like if it was a 6 and a 12 microfarad capacitor, it would be the same. Anytime I have two capacitors that are separated by a factor of 2, and they're off by a factor of 2, then I know that their voltages also are off by a factor of 2. All right? So I have 8 volts and 4 volts here. And then, if I have 4 volts across this capacitor, because capacitors in parallel have the same voltage, I know I have 4 volts, 4 volts, and 4 volts here. All right? Now, if the numbers don't work out that simply, the way that you would do this is you would find the equivalent capacitance of this, which we know is 2 microfarads, and then you would find the equivalent charge, which is going to be 24 microcoulombs, and then you would say I have 24 microcoulombs on each of these capacitors, because capacitors in series have the same charge, and then you could say, well, 24 and 6 gives me 4 volts. 24 divided by 6 is 4 volts. So all these little pieces have to fit together like this, and there are usually different ways when you're approaching a circuit to come at it. You can approach it in different ways in how you get to the answer. Let me step back through that in case you missed it. If I can't just look at this and say it's 8 and 4 volts, which hopefully by the time we're done with the resistors, you'll sort of have that ability. But if you can't just look at it, then you find the equivalent, which is 1 over 3 plus 1 over 6, which is 2. And the charge on the equivalent capacitance is 2 times 12, which is 24. So the charge on this 2 microfarad capacitor is 24. But capacitors in series have the same charge. So this 24 microcoulombs is also here, and it's here. Which we can see, right? Because 8 times 3 is 24. 6 times 4 is 24. So we have 24 microcoulombs on each of those. And then on the 6 microfarad capacitor, I have to have 4 volts. And then step back from there. All right? Lots of practice. They're like little puzzles that fit together. And so you have to know the rules first of all, and then you have to be able to apply those rules. Okay? We're going to see more circuits in chapters 3 and 4, which we're going to start on soon. And those circuits, chapters 2b, 3, and 4, will likely all be on the exam. You know what I like? You know what I like? What? You know those little Cokes, like they come in the little 8-ounce cans? You know what I'm talking about? Like we have those. My wife gets the Dr. Peppers and I get the Cokes. I like those. You know where they make them? Who gave away my punchline? Who is that? Camille? All right. Okay. Let's look at energy. We have one other thing on this little section, and it's really just sort of a little add-on, though it's kind of important because capacitors are nice because they can store energy. In fact, I'll show you a little video soon. But the purpose of capacitors is to store energy. In fact, capacitors really have two purposes. The primary purpose is to store energy, so you can put charge on a capacitor and then save it for later. Like that capacitor I passed around, the 4 farad thing, that huge thing. I assume, like I don't have a big whopping stereo system, but I assume that what that's for is, maybe you can correct me, but it's for when you got a big punch of bass and you need that little extra oomph of energy, it just adds that extra energy in. Does anybody do car stereos? Is it better for your car battery? I'm going to show you something in just a minute. That's pretty cool. Where somebody took their lead acid battery and they replaced it with a capacitor. But capacitors store energy, and that's what they're for. The energy stored is given by this equation. This is on your equation sheet. It's 1/2 CV squared. And actually, I don't know why people do this, but they do it. There are variations of this as well that are also on your equation sheet. You know, if Q is CV, then you can make variations of this. Gosh, I don't even know what they are. Let me look them up. They're on your equation sheet. Here we go, 1/2 QV and Q squared over C. So you can also have 1/2 QV and 1/2, what was it, Q squared over C? Yeah, Q squared over C, or Q squared over 2C. All right, so you can just substitute this into that equation and get these other expressions. Don't memorize them, of course, but if there's anyone that you memorize, just sort of know this. But it's on your equation sheet anyway. But if I want to know the energy that's being held by a capacitor, then I can just, if I know the capacitance and I know the voltage, then I can calculate that energy. So for example, if we have this capacitor, if I want to know the energy that's stored in the capacitor, I just say 1/2 CV squared. 1/2 of C is 10 microfarads, and then V is 2 volts squared, and so that's going to be 5 times 4, 20 microjoules. Notice that I carried my micro through. If you want to be careful about it, you can just convert this to farads, because that's the SI unit, but I carried it through my micro. So let's try this one. The way this might work on an exam is you just have a separate question like this. I ask you, what is the energy? Or I might give you a circuit that has a bunch of different capacitors, and I ask you the energy stored in one of the capacitors. And that becomes a more complicated problem because you have to figure out the voltage or the charge or whatever on that circuit, on that capacitor. All right, let's stop in about 10 seconds. On 105, or 104, let's say 104. So that's everybody, I think. Okay, good. A is right. It's really just sort of plugging in the right numbers, right? So I have 1/2 of 3 microfarads times 10 squared, 1/2 CV squared, so that's going to be 3. Actually, I want to convert this because all these are in joules. I'm going to convert it to 3 times 10 to the minus 6 times 100, and that's equal to 1.5 times 10 to the minus 4. Yeah, that's right. Okay, and that's in joules. All right. Let's see. Y'all know that in college, I know that many of y'all, like, you change your majors at various times, right? Well, some of you have, I know. But in college, I wanted to be an English major. Took all sorts of English classes. Really loved, like, I loved writing. I loved reading. I wanted to be an English major real bad. And that's actually true. And I also have a cat. His name is Frodo, and he's an awesome cat. I have a cat too. So that brings me to this question. Do you know what the difference between a cat and a complex sentence is? A cat has claws at the end of its paws, and a complex sentence has a pause at the end of its paws. Okay, let's go on. It's enough. Yeah. Chapter 3 is a really short chapter. We'll probably finish it, if not today, next time. And that'll get us ready for chapter 4, which is it's a big one, chapter 4, okay? I'll probably go ahead and put up your tutor assignment. It'll be due latter part of next week. But your tutor assignment for chapter 4. But it'll include sort of this material and chapter 4. Chapters 3 and 4 really come together. In this chapter, we'll talk about current and resistance. The good thing about this, especially if you're in lab, I know most of you are in lab, not all of you, most of you are, but the good thing is that you've already seen all this, much of what we're going to be doing in these next couple of chapters. And so you get a little preview of it in lab. You've already done resistors in series and parallel. You've already done resistance, that rho L over A. You've already done your voltmeters and ammeters. You've already done your Ohm's law. So that's good news. We're going to define a few more things. Current is the rate at which charge flows past a point. In a given time. Generally, when we say a rate, we're usually talking about a time rate. Not always, but sometimes, most of the time. And so the current then is defined as, we define this current as Q divided by T. I look in a wire, and I look at a particular point, and I ask myself, how many electrons are moving past this point in a given amount of time? And that is our current. And so the unit for current is the amp. This is short for ampere. We abbreviate it either as an amp or we can capitalize it because it's based on a person's name. And it is equal to, 1 amp is equivalent to 1 coulomb per second. So I have so many electrons that make up a coulomb every second, and that would give us an amp. In fact, if you're curious as to how we define the coulomb, what is the charge of the coulomb, that's how we define it. We define it based on the amp, giving us a current of 1 amp. I think we talk about that in the lab later. I'm not going to get into it now. Oh, shoot. I want to show you that video. Can I show it to you right quick? So before we get into this, it goes back to capacitors. Connect it in parallel and series, replace the resistor with the measuring device, or does it depend on the circuit? All right, I'm going to stop at 30 seconds. 30, I'll go to 33. 33. All right, awesome. A is right. In parallel with the resistor, let's look at the next one. Which of these statements is always true? This is a little more complicated. Think about it. Is the current through an ammeter or voltmeter small? Is the voltage across an ammeter or voltmeter small? Always true. Some of these might be sometimes true, but some of these, 2 of them anyway, are always true. So which of these statements are always true? Sort of assuming some things that y'all know here. I think you could probably reason this out, but most of you have had the lab and know that the voltage is equal to the current times the resistance. I'll give you another 10 seconds or so. Ask your neighbor if you're uncertain about this. Yeah, you are sort of spread out. Don't ask. Be careful about who you ask. Okay, I'm going to stop at 155. All right, yeah, where's are all over the board? So, look, the current through an ammeter is small. That might be true. Like if this is my circuit, I have a current going through it. It's true if the circuit has a small current. But if the circuit has a big current, then the ammeter gets a big current too. That's what it measures. So true maybe sometimes, but not necessarily. So not one. The current through a voltmeter is small. Look, big resistance, much bigger resistance than say this resistor. So we can think about our current that comes along here. It's going to take the path of least resistance. That's where they get that phrase, right? And the path of least resistance is right here. So that means that very little current comes here. So because of the big resistance in the voltmeter, the current through a voltmeter is always small. This is always true. Now, the voltage across an ammeter is small. V is equal to IR. What did we say about the resistance of the ammeter? Minuscule. It's like a piece of wire, basically, in that ammeter. An ohm, maybe, or I don't even remember what it is. It's very small. So that has a very small resistance. If my resistance is really small, that means my voltage is also going to be really small. This is always true for an ammeter, that the voltage across the ammeter is small. Now the voltage across the voltmeter, the voltage across here is the same as it is across here. Capacitors, we have the same thing. Caps in parallel have the same voltage. Well, it turns out the resistors in parallel, they have the same voltage too. Whatever voltage I have here, I have here. That's why we set it up like that. And so, if this has a big voltage, then this also has a big voltage. So 4 might be true sometimes if the resistor has a small voltage, but not always. So what's the answer? Oh no! Well, it's you 4 people, whoever you are. We're going to mark B. I'm sorry. Who was the 4? I'm sorry, gentlemen, but good job. And Madeline, too. Good job. All right, let's look at Ohm's law. I'm sorry, I will try to remember to change that. All right, let's look at Ohm's law. We've seen Ohm's law before. The flow of charge or current, I've seen it in the lab anyway. The flow of charge or current is proportional to the voltage. Remember, voltage is defined as energy for a charge. We saw that in chapter 2. Potential, we call this. Voltage is energy per charge. So if I have a lot of voltage, that means I'm giving a lot of energy to my charges. That's going to make them move faster. All right. So if they move faster, that means I have a bigger current. If a battery provides a greater voltage, it provides more energy to the electrons. Thus, there is a greater flow of current. So I, then, is proportional to V. If I have a big V, I have a big I. And so Ohm's law describes this based on the resistance. And it says that R is equal to V over I. Or usually, as we write Ohm's law, we usually write it as this. So like if you're an electrician and you use Ohm's law, this is probably how you think of it. That the voltage and the current are related by the resistance. The resistance describes how the electricity is resisted, how the flow of electricity is resisted. So for a material, if R is big, you need a greater potential or a greater voltage to produce the same current. All right, so imagine that you have a piece of copper wire. If you put 1 volt across it, you get a certain current. If you have a piece of wood and you want to get that same current, you need more than 1 volt or less than 1 volt to get the same current. A lot more, right? Because wood is not a very good conductor. You can get 1 amp of current through a piece of wood, but you need a really big voltage, and you probably burn up the wood anyway. All right, the unit for the resistance is the ohm. We use the capital omega, like this. And like I said, we often write ohms law like this. V is equal to IR. What's the unit for resistance? Ohm. That's another fun word to say, isn't it? You can say it again if you like. Go ahead. Ohm. Yeah, so that's the unit for resistance. Let's try this. 2 volts, 10 ohms, over 2 minutes, what total charge passes? Remember your Ohm's law, remember your definition of current. Y'all know we're going to Germany this summer? Did I tell y'all that? We're going to Europe. We've been planning for years. We're going to Finland, Paris, Germany. I don't care, do you? You're trying to do this problem, I understand. Go ahead. Oh shoot, we're almost out of time. All right. Well, y'all finish up. We have a few more seconds. All right, I'm going to stop at 120. Okay, good. A is right. In short, you first find the current, which is V over R. That's going to be 2 over 10, which is 0.2 amps. And then I is Q over T. So Q is 2.2 amps times the time, which is 120 seconds. So that's 24 coulombs. All right? Y'all have a great day. We'll finish this chapter next time and start chapter 4.